Hello friends, in this video let us use the circuit which is designed in previous video, how to obtain the frequency response curve for the single stage amplifier. Now the circuit is already designed using this multisim software by National Instruments. The circuit was designed, only I have added these labels. You can just double click on the segment. So if you double click on the segment, it will ask the color if we want change in the color of the segment along with the preferred net name that we can change. I have changed the color so that once the simulation is turned on, I will be able to differentiate and identify the difference between input and output waveforms. That's why I changed the color as well as given the labels to these waveforms as an input waveform which is taken from the AC signal source, AC power source we can say, and this here we are observing the output. So the negative of both the channels of oscilloscope, I made the color of that as a black, and positive are given the color codes as a green and red respectively for input and output waveforms. So if we simulate the circuit, so we'll be getting the details on this meter. This is AC voltmeter that gives us the RMS voltage for 35 millivolts. We are getting the output as a 546. So I have used these meters for displaying the value. So these meters I have chosen from the place indicators option. So if we go to any of the component list, now its simulation is running, so we are not able to see that. But if you place any component, from the group of the component families, there is one option that is a indicators, place indicators. So place indicators we can observe from the family only. So along with the transistor family there are indicators. From the indicators you can choose, these are the different indicators. So here from this I have chosen the vertical voltmeter. What is the benefit of this? Instead of using the multimeter as a voltmeter, from the instrument toolbar I need not double click and check its value every time. So as soon as you do the simulation, so we can observe its details. We can see the readings easy. That was the concern. So I replaced that multimeters by these indicators. Now if I double click on the oscilloscope, we get these waveforms. So I enlarged the window of oscilloscope so the waveform details can be observed easily. So this is the oscilloscope. So already we have seen in the oscilloscope, green color indicates input waveforms which is connected to channel A, where we are measuring its amplitude with the scale of 50 millivolts for every block. This indicates 50 millivolts per division. So for the amplitude, this complete one block. So this whole division indicates the 50 millivolts. So input is around 50 millivolts peak voltage. That is what we have chosen from the AC power source. 30 millivolt VRMS equal to 35 into root 2 equals to peak voltage of almost 50 millivolts. So one block is covered vertically. So 50 millivolts plus 50 millivolts, total 100 millivolts peak to peak is the voltage that we are providing as input. And output which we are observing at the channel B with the red color is, its scale is 1 volt per division. So if I increase its value or decrease its value, see it indicates here. So how much is its value? So from using these two cursors we can check the details of time period, and from that we can calculate the frequency value too. So if I drag the on to left side, so I am able to get the details. So from the channel B, 500 millivolts is the value for one division. So this one vertical block, this square blocks indicates one division. So one division carries the 500 millivolts as its amplitude. So from this also we can take the measurements of input and output voltages using the oscilloscope reading. So already in the previous video we have seen the waveforms. Now what new we are going to study here is how to obtain the frequency response for this single stage common source amplifier. So for the convenience I have given the proper labels. So when we go for a simulation with AC analysis, it will take these segment labels or the node levels as a reference voltages. So it becomes easy for us to understand. So go to the simulate menu bar. From that analysis option, go for the AC analysis. So in the AC analysis indicates for different values of input frequency how output parameter which is specified here is obtained. So how the input frequency is varying? Input frequency by default, whatever the values are there, I am keeping it as it is. So the AC analysis starts with starting frequency of 1 Hz and stop frequency of 10 GHz. Practically, actually, it is not possible to have an instrument which will give us this much variations of input frequency. It's not possible practically, but virtually with the simulation we can analyze the results. So it also asks the option, vertical scale, should it be linear or should it be decibel? So initially let us choose the vertical scale as a linear scale. And output parameter. Already I have added expression. I will remove that and rewrite again. Now, considering that frequency response curve is nothing but a curve which gives us the details about how voltage gain of an amplifier varies with respect to variations in the value of input signal frequency. That is what the frequency response curve. So voltage gain is nothing but output. It's a ratio of output voltage by input voltage. Let us design the equation. Output voltage. I want to add the expression first of all. So I will click to the add expression, and then in the add expression it will ask me the variables to be added. Output voltage. Copy this variable divided by divider operator. Copy this dividing function to this expression. Then Vout will be divided by Vin. Sorry, it's a power Vin. I want the input voltage Vin. So copy this variable to the expression, make it OK. So this is the expression that is added. So when I am specifying the variables in the output parameters, so it indicates for these values, this parameter, the input frequency variations will be there on x-axis, on y-axis will be getting the scale that is relevant to the voltage gain ratio, that is Vout by Vin. Now if I simulate this, so I am getting this graph. So these are the cursor details. If it is by default you may not get it. So I will tell you how to obtain these curves. Okay, this is the initial graph what you will observe on the screen. Now I will change its background to white so that it will become easy to make the readings, make a note of readings. Now this is a vertical scale is a linear, while the x-axis scale, this is a logarithmic scale. It was given by default in the AC analysis. X-axis takes the logarithmic scale, not the linear scale, so as to cover the wider range of the frequency, which is varying from 1 Hz to 10 GHz. Now I will click over here, show trace lines and data points for all traces. So for this graph, for the second graph, if I click here and if I choose this option, so it gives me the details about all the data cursors. Now if I click on show cursor, so this is show cursor option. So it gives the cursor details. Cursor details are given in this window, and these are the two cursors, second cursor and the first cursor. Similarly, this is the phase plot and this is a magnitude plot. Magnitude of the voltage gain versus frequency, phase of the output waveforms with respect to input variations frequency, input variation in frequency. How to obtain the bandwidth, that is a major concern now. So if you observe for this particular part, almost for wider range of the frequency range, we are getting the constant voltage gain. So what is the value of voltage gain? So now this is a cursor 1. So you observe this table, as soon as I move this cursor 1, it makes the variations in x1 and y1. So x1 is 1.5k. If I want to check the value of this at 10k, set x value to 10k is the option. So if I set the x-axis value to 10k, the cursor goes to 10k. So x1 indicates 10k. At x1 I am getting the gain constant and higher value, with higher value equal to 15.731. Now to obtain the bandwidth, we have to find the numerical value which is 70.7% of this value. So 70% of this value, Let me check if I can get the calculator here. I will take the C. So calculator, this is a calculator. Let us find the 70.7% of 15.7310. So 15.7310 into 0.70, this is the formula actually, standard way, equal to, it becomes 1.22. Okay, fine, 1.22. Now we can drag this cursor and find where we are getting the 1.22. Or let me check if allows, set x axis, no, y value to 11.22. Let us check if cursor appears. So 11.22, it has come to this value. So if we take this one, this also can be set to this value. Okay, sorry. So right click, set y value to 11.22. Let us check if I can get perfect. Okay. So 11.22. See, actually dx is nothing but it's a x2 minus x1. So here x1, first cursor is on to the second side and second cursor has down to the initial values, and that's why difference is indicated to be okay. I will change the cursors. I will bring, so this is second in between cursor. If possible, I will. Okay. 11.22, and the first cursor is 11.22. Second cursor 11.21. So dx is indicated to be 5 megahertz. So what we have done is, so we can have the data levels also. So for more details, if I will add data level cursor, so at this point it will give me the data levels. So I will take this on this side and this window over to this side. Similarly, we can have this add data level at this cursor. So it is giving us 11.22. It should be 11.22. Okay, 11.07. It should give us data label 11.22. This is perfect. Okay, 11.22. See, whatever is the maximum voltage gain we've obtained when the vertical axis is linear, we obtained. So the bandwidth, how to obtain this? Now this becomes F2, this becomes F1, or this becomes upper frequency minus lower frequency. So these lower cutoff frequencies are decided by 2 coupling capacitors and 1 bypass capacitor. And upper cutoff frequency is decided majorly by the internal capacitances of the transistor, that is for the of the MOSFET, which has the multiple internal capacitance that also plays important role in deciding the corner frequencies. So in this way, difference between these two gives the bandwidth of this amplifier. Now if I coming to this phase plot, if I click here with the cursor, show cursor option, so these are the cursor details, and these are the two cursors. So using this graph also we can obtain where we are getting exactly 180 degree. So if I right click here, add the data label, see what it indicates. At 16.06 kilohertz of frequency I am getting the phase shift of 179.97. So at these points, so the transition occurs from this to this. So here if we take the details of this point, this particular cursor, let us check if we can take. I will bring the cursor, first cursor onto this point. So if we take, how much it should indicate? Negative value. So add data labels to this cursor. So it is giving me the details. Okay, minus of 149. So somewhere, so minus 180. So onto this side, so first cursor, okay, it's not dragging now. I think it has hanged because of multiple attempts. Okay, fine. So this is cursor 179. See, if you see details over here, it is giving minus of 179. So I am getting here the 180 degree phase shift. Plus or minus, it is okay. So for 10K, 10K I am getting the minus 180 degree phase shift. So this is a phase plot. So if we